you would have had, it traveled in the air with speed ds. But then the wind carried it an additional distance, dw. So if you'd stood still, that long a chain would have gone by. In other words, if you were standing beside the road, that's the length of chain that would have gone by in a second. But you didn't stand beside the road. Instead, you moved forward by a distance vt. So what length of chain actually went by you? That, which is Vs plus Vw minus Vt. So, how many beads reached you in a second? Well, the number reaching you in a second, which is the frequency that the truck driver would observe, is the length of chain that went by, Vs plus Vw minus Vt, divided by the spacing, which is what we found up here. And so, it is Vs plus Vw minus Vt, divided by Vs plus Vw minus Vc times f0. And if the truck and the car were going with the same speed, there'd be no effect. If they aren't, there's an effect. Okay? Well, now we have a little bit more subtle question to ask, and that is, what is the wavelength that is produced by the waves bouncing off the truck? So, to analyze that, we do exactly the same thing. We just look carefully at the first and last bead bouncing off the truck. So, here's the truck. Now, the first bead bounces off the truck at the beginning of the second. It travels a distance Vs in the air, but the wind pulls it back by an amount dw. So at the end of the second, the first bead to leave the truck is right here. Where is the last bead? Well, it's just leaving the truck now, so it is where the truck is. So the space between the first bead and the last bead is this distance, which is Vs minus Vw plus V truck. That's the distance occupied by how many beads? The number of beads that hit the back of the truck during the second, which is this number here, which we'll call F truck. So, the wavelength coming off the truck is the distance, Vs minus Vw plus Vt, divided by the number, which was Ft. And therefore, the wavelength leaving the truck is Vs minus Vw plus Vt, divided by Vs plus Vw minus Vt, and then you'll have Vs plus Vw minus Vc divided by F0. So that'll be the wavelength in the air coming back toward the car. Making sense? We're just systematically looking at what happens at each interface. Now the last one is what you hear. That's the frequency of the echo you're going to get. So, to analyze that, what's going to happen is, here's the car. Now, and during the second, the first bead would go a distance Vs, ask you, but the wind hauls it back by a distance Vw. So the first bead to reach you is now located at this position. When the last bead reaches you at the end of the second, it is where you are, and you have moved forward by a distance Vc. So the space between the first and the last beads is Vs minus Vw plus Vc. So how many reached you? The length of the chain that went by you divided by the spacing between the beads on the chain, which is the thing we calculated here, and the truck. So the frequency of the echo, which is the number that reached you in a second, is the length of chain, Vs minus Vw plus Vc, divided by the spacing of the truck. So, putting it all together, frequency of the echo is Vs minus Vw plus Vc, divided by that stuff. And so we have Vs plus Vw minus Vc, and then we have Vs minus Vw plus Vt, and Vs plus Vw minus Vt times F0. And so that'll be the frequency of the echo. Now any Doppler effect problem is done exactly this way. Just whatever the situation is, just analyze each of the steps involved, and you come up with the answer. Nothing mysterious. Now, this is interesting. Has all sorts of practical applications. That's the way radar guns work, for example, for speed traps and so on. But from our standpoint, more interesting is its role in astronomy. Because the same effect happens with light. It's a little more subtle because of relativity, which we'll be talking about shortly. But the basic idea is exactly the same. If a source is moving toward or away from you, it will shift the wavelength of the light that you receive. And that's how we measure the velocities that different galaxies and stars have with respect to us. And that's an absolutely key ingredient of getting the dimension scale for the universe. Because what we do is, by looking at stars that are known distances away from us, fairly close, we can establish a relationship between the size of the frequency shift, called the Doppler shift, that you have in particular wavelengths. Stars emit, as we'll see when we look at quantum mechanics next semester, the emission from atoms isn't continuous. It's a series of lines. Certain frequencies are emitted by hydrogen, different frequencies by helium, and so on. And so you look at a particular line pattern, and you observe the frequencies it's at, or wavelengths, whichever one you want to look at, compared to where it should be. And that gives you the velocity, because of this Doppler shift. It's called a redshift. It gives you the velocity that the emitter has with respect to you. Now, in very interesting fashion, we're able to establish a curve that relates the velocity the galaxy has to the distance it is away from us. And we can do that out to distances of the order of many hundreds of millions of light years by looking at variable stars and things. Beyond that, what you do is you get the distance by looking at what the velocity of recession is, looking on your graph that plots velocity versus distance, and that gives you the distance to this receding galaxy. And that's how the distance scale for the universe is established. We'll talk a lot more about this as we get more information as we go along. But that's the fundamental reason from astronomical uses anyway, why the Doppler effect is important. But it's a universal phenomenon for waves. What does it fundamentally rely on? It relies on the statement that the propagation of the wave is determined by the medium it goes in, it moves in, not by the source or the receiver. Velocity is just determined by the medium it propagates in. That's the fundamental assumption in this. And we've determined that because we've determined how to calculate velocities. And the only thing that was necessary was the properties of the medium. The source or receiver had nothing whatsoever to do with it. Making sense? All right. Now, we're going to start this now, and as mentioned, what we're going to do next. Next, we're going to look at propagation of waves where one or more waves intersect one another. And we're going to ask, what happens when two waves collide? And the conclusion we're going to make is that as long as the disturbances are not too big, they add algebraically. It's the old assumption of superposition, things are linear, and that's a statement that's true provided the displacements aren't too big. You take the wave, when the thing's oscillating on the spring. If you put 1 kilogram on the spring, it's stretched 6 inches. You put a second kilogram on the screen, on this spring, it's stretched another 6 inches. They added. If you put 100 kilograms on the spring, the thing suddenly distorted and broke. They no longer added. So as long as the displacements are relatively small, you expect them to add, things to be linear. Now, we're going to look at what happens in that situation. And that will be true the vast majority of cases, but not all. I mean, you can create situations where it's nonlinear. You get solitons and sonic booms, and you get a variety of things which are results of nonlinear behavior.
The soliton.
Yeah. What?
What's the soliton?
Well, that's an exotic wave that can reach huge amplitudes because it is not a linear process. We're not going to go into the mathematics of that, but it's an interesting thing to read about. I probably won't have time to talk much about them, but you can look them up on the internet. They're fascinating. They occur, I mean, they're rogue waves in the ocean, for example. But we're going to deal with the linear situation. In electricity and magnetism last semester, we'll come to this phenomenon. When it becomes nonlinear is when the energy stored, i.e. the amplitude, the energy was amplitude squared. When the amplitude of the electric fields becomes big enough, all of a sudden that energy can convert into making particle and antiparticle pairs, like the spring breaking. You add energy, the amplitude doesn't increase, suddenly it goes away completely, and you get a particle and antiparticle pair. So in all of these situations, this assumption of linearity is good for a wide range, but not for all. We're going to deal with the case where superposition works. So we're going to look at interference. First, we'll look at just two waves moving in opposite directions on a string. That'll produce standing waves of musical instruments. And then we'll look at interference in general. Now, this week, I'm going to be doing all of them, so it'll be a lecture again tomorrow, but in the usual place. Then, right? Okay, have a great day.